Welcome to Power System Protection Lectures. My name is Pratap Mysore. Today we will be talking about transmission line protection. This is the third lecture out of four on this particular topic. We just covered last time what are the inputs to a transmission line distance relay, where your voltage is one of the inputs and current is another input. You have a PT which steps down the transmission line voltage to 115 volts or 69 volts, which is the nominal, and then the current is stepped down from the rated transmission line current could be through 2000, 3000 amps to 5 amps under nominal current. And also we went through what is the relationship between what the impedance that the relay sees and the actual primary line impedance. We came up and said that the secondary impedance, what the relay sees, is related to the primary impedance by this equation: Z secondary equals Z primary times CT ratio divided by the PT ratio. Then we took an example of a 69 kV line, which has got 35 ohms. It's a 50-mile long line, and it has got a CT ratio of 600 to 5 and PT ratio of 600 to 1. So the CT ratio divided by PT ratio is 0.2. So the line, the secondary ohms is 0.2 times 35 ohms, which is 7 ohms. So if the relay measures 7 ohms, and then the fault is where? The fault is at the end of the line, which is 50 miles away. The relay gets the name distance relay because the impedance is directly proportional to the length of the line. And then, your primary impedance is based on the impedance per mile when you looked at those calculations also in lecture 1. Now let's look at what type of faults are there in a three-phase system. You have A phase to ground, B to ground, or C to ground. These are called single line to ground faults. Or it could be between phases. It is A to B, or B to C, or C to A fault. These are called line to line faults or phase to phase faults. And then, or you can have two phase to ground. It can start like a single line to ground fault, and then if it is arcing, it can arc over and create two phase to ground, or it's called double line to ground faults. And then finally, if all three wires they are shorted, then it becomes a three-phase fault. So if a three-phase fault is there, if you connect a ground or if you don't connect a ground, it doesn't matter, because if you add three currents, IA plus IB plus IC, it will be equal to 0. And this assumption is true if we have a very perfectly balanced network, which most of the cases may not be. Even though that there are three, the three-phase short, you can get an unbalanced current, which is a negative sequence current or a zero sequence current. So it depends whether you have with ground or without ground, because zero sequence current doesn't flow into the earth. And this comes only because of the system asymmetry. Otherwise, if in a balanced network, a three-phase fault, whether there is ground or no ground, it does not matter. There's also called cross-country faults. If you look at a grounded system and an ungrounded system, in an ungrounded system, if there is an A to ground fault, the voltages on the other two phases goes to line fault, line voltages. So this excessive voltage might cause a flashover at some other point. It could be in front of the relay, or it could be behind the relay on some other phase. So you have an A phase to ground fault at point location A, and B to ground fault could be in a location B, which could be either in the front or in the back. These are called, because these two faults are at different point locations, these are called cross-country faults. Then what does the relay do? It compares, it calculates, it has a voltage V, and then it creates another compensated voltage, as we call it, V minus IZ or IZ minus V, and tries to compare the phase angle. That is what we covered in the last lecture. This is a simple example. Then there are a lot of more complications, like you add a memory. If the fault is very close, when one of the voltage becomes 0, then what does it compare with? So there are different techniques. If you read through the relay catalogs on distance relays, they cover more into that. The basic concept only I wanted to just introduce so that you can go back and read more papers or textbooks which cover a lot more. The goal is to measure the same impedance up to the fault point, irrespective of the type of the fault. That is what our intent is. So how many faults are there? You have three phase to ground, three phase to ground, and then you have three phase to phase, and then you have three phase faults. There are 10 types of faults. If there is a fault at 50% of the line, irrespective of the type of the fault, when the relay says, for example, if we take 69 kV, it's at 35 ohms, right? And then it measured 7 ohms. If the relay measures 3.5 ohms, it should be the same value whether it is a single line to ground fault or a phase to phase fault, or it is a three phase fault or a double line to ground fault, if the fault is at the middle of the line. So that is the intent. So now we will look through what inputs are required for this relay to measure actually the same impedance up to that fault point. Let's look at it. The relays essentially measure the positive sequence impedance of the line up to the fault point. This is the basic intent of our design, is that the relay should measure only the positive sequence up to the fault point. So now A phase to ground distance elements, they use A phase voltage and IA plus K0 times IN. I introduced that zero sequence compensation factor some time back. If you take the positive sequence impedance, then the ground impedance is K0 times positive sequence impedance. They derived some value when we were looking at the line parameters. It is nothing but 1/3 of Z0 minus Z1 divided by Z1. So if I give an A phase to ground measuring unit, the voltage input is VA, and the current input is IA plus a portion of the neutral current, IA plus IB plus IC. That is what I'm adding to this. For a B phase, if I use VB plus IB, VB and IB plus K0 IN, and C phase VC and IC plus K0 IN. When I feed to three measuring units, one to detect only A to ground faults, one to detect only B to ground faults, one to detect C to ground faults. If I give the ratio, if you take the ratio of VA to IA plus K0 times IN, then what it measures is only the positive sequence impedance up to the fault point. And similarly, if it is a B to ground fault, this particular element which has got B phase faulted voltage and the faulted current plus some compensated current from the neutral, if you take the ratio of these two, it measures only the positive sequence up to that fault point. For a C phase to ground point at the same location, I need to use another measuring element which takes the ratio of the C phase voltage to C phase current plus certain amount of neutral current. And similarly, if I want to measure the same positive sequence impedance up to the fault point, for a phase to phase fault, I have to take A to B fault, I have to take faulted phase voltage across the voltage across the faulted phases VAB, and then IA minus and IB. IA minus IB, the two currents that are going in. In a phase to phase fault, one current goes on one line and then comes back on the other line. So then it is the difference in the two currents. That is what we are looking at it here. Take that for measurement. So if I take VAB and divide it by IA minus IB, it measures the positive sequence impedance up to the fault point for an A to B fault. If I want measure the same impedance for a B to C fault at the same location, I have to use VBC and IB minus IC. And then for C to A, I should use VCA and IC minus IA. So if I want to detect three types of ground faults, I need three measuring units, which each one has got A to ground voltage with the compensated current of the A phase, and B to ground for and then compensated B phase, and C to ground for compensated C to current for the C of the C phase. Similarly, for a phase to phase, I need three more. So I need 6 measuring elements to detect 3 phase-to-ground faults and 3 phase-to-phase faults. So line to ground fault can be detected by any one of these. Okay, so essentially I need 6 distance elements needed to detect all types of faults. Three-phase faults could be detected at a single line to ground fault or a phase-to-phase fault. And then double line to ground fault can also be detected as a line to ground fault or a phase-to-phase fault. So essentially, I need 6 measuring elements to detect all types of faults. So now, if you look at the way I want to set it, if I have a line which is 50 miles, that 69 kV line, we took an example, and then if I want to set the relay so that if it measures 7 ohms, that was the secondary impedance of that particular line, and if it measures less than 7 ohms, then I say if I trip, if it measures greater than 7 ohms, then I can block, just to say that the fault was within this line section or outside the line section. But we need to look at the errors in measurement, because we are basing all our decisions at measuring at only point A at the relay location. So it is 50 miles, it can have a tolerance of plus minus 10% or 5% or 2% depending on the accuracy. You have errors in your uh, calculations of the data. When you look at the line parameters data, it uses the resistivity of the line, and then that may not be accurate. It depends on whether it's a wet area or it is a dry area, and then your assumptions may or may not be very accurate. So we need to look into that. And secondly, you have uh, CT and PT errors. So that also produces, you have accuracies, C800, I covered CT accuracies and PT accuracies in instrument transformers. So we have to account for that. And the measurements in the relay itself has some accuracy. If you look at this, and then line impedance calculations are there, you cannot go from point A to point B and then detect accurately for faults at point B. We don't know whether it is on the line or behind the breaker at the remote end or beyond the line section AB if it is very close to the station B. So based on this, we set the relays with about margin of 15%. So when we say when the relay is set to operate without a delay for faults up to 80 to 85% of the protection line, we call this as an underreaching zone. Let me repeat this. You don't intentionally delay the tripping if the measured impedance is about 80% to or 80 to 85% of the impedance of the line. Now let us again take the examples of that 7 ohms. So 0.8 times 7 is about 5.6. So if the relay measures 5.6 ohms, I know for sure the the fault is on the line, because that 15% I am allowing this for the error in the parameters, CT ratio, PT ratio, and also the relay design errors. So if the relay measures an impedance of 5.6 or less, I say that definitely the fault is on the line. I trip this. So now this is called zone 1 in relay terminology, or it is also called underreaching zone, because you're setting the relay to a value less than 100% of the line section. So it is not reaching fully, it is underreaching this line section by 15% if you take this example of 85%. Now, 15 to 20% of the line, what we do is, again, let's look at this. This zone 1, I need to have 6 measuring elements, 3 to detect phase-to-ground faults and 3 to detect phase-to-phase faults. They also detect phase-to-ground and 3-phase faults also. So now, in order to cover the next 15% to 20% of the line, I use another set of these 6 elements. What is happening here? Yeah, 6 elements, and then we set this about 15 to 20% more than the A to B impedance. That is, if there is an error, I just want to make sure that I detect all the faults in line section AB. but this is set beyond the reach, beyond the line section. So it is about 115 to 120% or 125% of the line impedance. So if you do that, this is called an overreaching zone because it is reaching beyond the lines, beyond the remote end. And then we try to time delay this because we are not sure whether this fault is in adjacent line section, where that will have a zone 1 relay which will trip. If it doesn't trip, this provides a backup for that. So if you look at it, essentially a relay at A, it covers, it operates for all the faults up to 85% of the line section, and then 85 to 120 to 125%, 115 to 125%, it is what we call zone 2, that provides some sort of a backup for this zone 1 relay from the section BC. And then you can also use a third zone to cover beyond this line sections. That means it covers from section A to B, and then it provides full backup for the adjacent line section BC. This could be a short line, or this could be a long line, or station B might have several lines. In such conditions, zone 2 is set to underreach the zone 1 of section B by of the shortest line section of the line going out of B, and then zone 3 is set to cover the 100% of the longest line section of the adjacent line. This is just an introduction of the concept here. Just go through these slides and try to understand what we are trying to do. We don't set the measurement here, the instantaneous relay, to operate for all faults in the line section. We just give a margin of 15% because we are not sure whether the fault is here or it is beyond B, beyond the remote station. So then we use a second set of relaying, and I've shown this here, that is sitting here at station A, and that has got a time delayed function, and then that will operate with a certain time delay, providing backup protection for the relays at station B looking into the adjacent line section. You can also have zone 3 on that. Okay, so now if you look at it, this is how we set the relay. Zone 1 is typically set at 80 to 85%. Zone 2 is set to at least 115% line to account for the errors. Typically you set to 125 to 150. Zone 3 is set to 125 of the adjacent line section. Adjacent line section, as I said, it could be a very long line section, and we try to cover the longest adjacent line from station B. That is adjacent line at B, that is from any longest line from station B in our example. There is what is called apparent impedance effect, in-feed effect. Here we know that if there is a fault here, the impedance seen by the relay is ZF, ZAF. Now the voltage at the relay is IA times ZAB, the impedance of the line section from A to B, and then plus IA plus ID times ZF. This is the impedance, right? So now this, if you take the voltage drop across this, it has got impedance times the sum of these two currents, but here we are taking only one current, so it measures a higher impedance. So if you look at it, the measured impedance from A is the actual line impedance plus the actual impedance up to the point, and plus a factor which is increasing that ZF by a factor which is a ratio of the remote current to the local current, ZA plus ZF. So impedance seen by the relay, as you see, is higher than the actual impedance up to the fault point. Okay, so this is called the apparent impedance. Similarly, the relay at D also sees an impedance higher than the actual impedance from up to the fault point, and that is given by ZBD plus ZF plus IA by ID times ZF, right? That is IA divided by ID times ZF is additional impedance. So when you are trying to cover backup, you set zone 1 to cover only up to 85% of the strongest section, and zone 2 is if you are trying to cover zone 3, if you say that if you are trying to cover the adjacent line section, you have to make sure that you should take into effect of the in feed. That is, you have to set it higher than the actual impedance up to the fault point. Okay, this is another example I have provided here to give you how do we set for a three-terminal line. So the zone one is suppose if A to B, A, B, and C are three stations there on a three-terminal line, and then you measure the impedance from A to C and A to B. And zone one is always set for the shorter of the two line sections because you don't want to overreach if one end is open. And zone two is covered for apparent impedance of the longest line section. Okay, so it's just an example. You just have to go through this. It looks simple, but or it looks very complicated initially when you look at it. Just go through these slides and try to understand how to set these relays. Now here is another example. You set zone 1 and zone 2 to cover all the lines, the faults within this line section A, B, C. But you find that when the breaker at C is open, the zone 2 tries to reach beyond the adjacent line section from B to D. This is a short line, and this is, for example, zone 2 is set as an apparent impedance, which is very high. Then what you have to do here is you have to extend your line, your time delay coordination. You have to increase it to take care of the settings. Okay, sequential trippings. If the ratio is very high, then you can the setting of the relay is very high, and then what you do is you open the breaker at one, allow the breaker to one relay to see the fault. As soon as one relay one end opens, it becomes a two-terminal line, and then it operates after that. This is called the sequential tripping. What are the key things which we come out of it? Zone 2 and zone 3 settings, over each zone should consider apparent impedance, especially for three-terminal lines for zone 2. And then zone 3 is 100% of the line plus 125% of the adjacent line section. If it is not possible, then you have to allow sequential tripping. The factors that influence distance relay and operations, you can look at it. There are parallel lines, effect of mutual impedance to ground. Current reversals are there when there is a parallel line. As soon as one end of a line opens, the current reverses and tries to go on the other line. That might cause operation. Series compensated lines have got special issues such as voltage inversions or current inversion, and then effect of load also has some impact on the settings, on the operation, and especially if it is a long line and then you have to select so that you don't want the relay to operate under load conditions. There is what is called outer step situations also, which we are not covering in the basic courses. So essentially, we try to go through some of the basic concepts of how the relays are designed and how many elements are needed. And that is what the intent of this particular lecture was. And then we have gone through a setting example here. Please do go through this and try to understand how the relays are set. So essentially, you have a positive sequence impedance and zero sequence impedance of different line sections here. And then you have the CT-PT ratio. So what we do is we first, our philosophy, we have to say that we'll cover 85% in zone 1, and zone 2 will cover 125% actual impedance. Zone 3 we cover with apparent impedance. So we set up the philosophy and go about doing the settings. Zone 1 is set to 85% of this. Again, the relay is set on the secondary side of the instrument transformers. So you have to account for the conversion of the primary impedance to the secondary impedance. And zero sequence compensation factor also you have to set, because as I said, phase to ground faults measurement uses this zero sequence compensation factor. And the zone 2 reach is set to 125%. And you can either use, if there is some variation in the impedance of the zero sequence, K0 setting is also possible as an option in certain relays. And then what we have to see is whether it overreaches the remote end. It could be 100 miles followed by a 5-mile or 10-mile long line. So under zone 2, it's 125% of the 100 miles, which can overreach that. So it can operate, if there is a fault on the adjacent line section, it can operate also. So you have to cover for that. Okay. Uh, Forward reaching zone also we have covered. I'm trying to just go through this because this is a recorded lecture. You can spend your time looking at each one of these and pause it, and then spend some time to understand how this is done. So in the next lecture, we'll try to cover about how do we increase the operating time if the faults are in the last 15% of the line section.